Here.
So the seminar is Self-Gravitating, Superconductors, and Contact Geometry. So Cesar, go ahead.
Right, let me share the screen and let me know if it works. Can you see that?
Yeah, that's okay.
Excellent. Well, yes. First and foremost, I would like to thank the organizers for inviting me to present this talk, especially for their hard work during this particular time of pandemic. And it would have been nice to see all my good friends in person. But anyway, so this is my talk for today: self-gravitating superconductors and contact geometry. So it might sound for someone perhaps like a very exciting title, or I hope at least interesting. But the fact is that it's a self-gravitating superconductor in three-dimensional gravity, which happens to be topological and massive. And that doesn't seem to be the case of our universe, right? So from the point of view of the meeting itself and the era we are in, general relativity and gravitational theories, this seems like a far-fetched kind of idea. But let me explain and give a little bit of motivation of why is it worth studying this stuff. Even though the space-time we inhabit is certainly not this one, and if it were, it wouldn't be certainly a superconductor. So before I start, let me say that this is work I've been doing together with Daniel Flores and Marco Maceda, and also stemming from the discussion in the previous day. I was trying to motivate this talk, but I think you all guys helped me a lot to find my way around motivating this kind of topic, which in the era of patience seems a bit far off. So yesterday you were asking, is it worth modifying gravity, or should we modify it or not? And instead of asking that, let me ask the following question: shouldn't we apply gravity? This is a topic I hardly ever come across, but I've come across ever since I started working with engineers. So what is it gravity good for? What have we learned about all of this? And it has already been over 100 years since general relativity saw its first lights. This year, the Nobel Prize has been awarded once more to a predicate of such a worldview: black holes and singularities, ubiquitous in geometric theories of gravity. Moreover, earlier this decade, right after the centenary of general relativity, gravitational waves were finally detected. Cosmic background radiation had been responsible for a few words. I mean, it's all over the place. It appears that right now, and that has been the topic right now, we're in a new golden era of gravitational physics with new data and new observations of this. But every once in a while, especially the younger ones, will face the question, especially these days, in these particular times, what is gravity good for, actually? I mean, surely it has deepened our understanding of nature. It has pushed the boundaries of our conceptions to the very beginning of our universe, and space and time, its boundary or non-boundary or whatever you want to call it. It has shown us actually that catastrophes may, and indeed they do occur as forming singularities. So we understand quite a big deal about it. But really, given the problems humanity is facing, what is gravity good for? And we can answer these in at least two things that I can imagine. Is that, well, undeniably, if we're going to survive as a species, it will be relevant. in terms of space exploration and energy extractables and all this stuff. But what people really mean is, what is it good for right now? What are the applications of general relativity? And here it comes, as everybody would claim, well, the GPS in our mobile phones actually works because of general relativity, and it has allowed us a more efficient, more secure navigation in space and on the Earth indeed. And that wouldn't be possible without our conception of gravity. But that even with that application, which is actually truly amazing, it seemed that it falls a little bit short in terms of application, right? I mean, what do I mean short? Well, you may say, I mean, gravity, general relativity in particular, is perhaps one of the purest endeavors of human imagination. But you could praise the same as gravity as one of the most far-reaching, beautiful ideas there are. So why is there so very little application, say, compared to electromagnetism or quantum mechanics, indeed? So this discussion may carry on for a while, to the point that somehow GR, despite all this success and all these far-reaching ideas, is nowhere near as successful in applications, in practical applications, as the other fundamental theories. Say, Maxwell's theory of electromagnetism took less than 50 years to be widely applied and transform the way we understand our living in a daily basis. And same goes for quantum mechanics, where in less than 50 years, you pass from black body radiation to understanding how the atomic transition works, so to make a transistor and circuitry based on that. And why is it the case? I mean, why haven't gravity been that applied or been that successful? And in my view, it comes to the fact that in both electromagnetism and in quantum mechanics, we are not mere observers of the things that are actually happening. For instance, in electromagnetism, we control the way the fields are generated and propagate across the grid. And same goes for quantum mechanics. We build gates so we can perform computations. But in gravity, it appears that we are very, very passive. I mean, we're just observing what the universe provides us, and we cannot control the gravitational field in any way so that it suits our needs. So that surely explains why we haven't applied all these ideas, which are absolutely groundbreaking, to everyday life. And as you may expect, my whole contention is that that is absolutely wrong, right? The funny thing is that, as far as I'm concerned, probably I haven't read a lot, this is not very often permeated among the student community and the people can actually do by knowing gravitational theories. But let me begin with the motivation for the work I'm presenting today. So it's kind of the Eddington effect. So back then, we're talking about the 20s, people already said, like, influence of matter on electromagnetic phenomena is equivalent to the influence of a gravitational field, right? And that whole thing, that whole idea was the birth of a new class of science, of applied science, which is metamaterials. Can we engineer materials so that light propagates on them as it would be in a gravitational field in all sort of ways that we would render because of astrophysical interest? But in metamaterials, that would actually be really, really cool. And that's what actually people do to build invisibility cloaks and like. So in Jackson's talk earlier, while listening to teleparallel gravity, actually came as a really good surprise, because time and again, people try to vindicate why teleparallel gravity is so cool and exciting, and it really is a really cool theory, a geometric theory. But it turns out that back in the 30s and 40s, some guy named Gabriel Crom actually applied teleparallel gravity and torsion theories to understand rotating machines. in electrical engineering. And that was not obscure research. I mean, the Princeton, the Institute of Advanced Studies in Princeton and General Electric were actually quite interested in it. Einstein was interested in it. Von Neumann was interested in it. And it appears that teleparallel gravity or torsion theories are the tools needed to understand and control machines such as electric generators plugged in to our new renewable sources of energy. So, I mean, I spent already 10 minutes trying to motivate this thing. I think I'll be kind of the first person to speak of renewable sources of energy in a Earth-based system in a gravitational and cosmology seminar, but it is the case. Teleparallel gravity actually works in electrical engineering. It's exactly what we need to control the uncontrollable sources of energy like wind or waves. So the problem there is stability. And it turns out that the stability problem is actually written in terms of an equation we saw earlier today, which is the geodesic deviation equation, but in terms of teleparallel gravity. It's exactly the same equation, exactly the same dynamics. But in this case, it refers to perturbations in the electromagnetic system as opposed to free particles in a gravitational fields. But the problem is actually the same. So to make it brief, we do live in a golden era of gravitational physics. We have plenty of new data coming from experiment and observation, and we heard this through the week. And it has also been applied to the everyday life by understanding how GPS works. But there's another branch of applicability of these same ideas that I think in the community is heavily unexploited, which is the science of metamaterials and science in electrical engineering, right? So the talk I'm presenting today, just to remind you, is about a superconducting theory in three-dimensional gravity with a topological mass. So what is it? It's certainly not a theory of space and time in terms of gravity and the universe we live in, but it's certainly a theory that helps material scientists to understand a yet unknown phenomena, which is superconductivity. So the talk I'm presenting right here is somewhere in the middle between metamaterials and electrical engineering. So I hope this serves as a motivation, especially for the younger people who are not facing an easy time ahead in their academic careers. Sorry. But anyway, now to the real physics part. So there are three sets of words in this title: self-gravitating, superconductors, and contact geometry. So let me begin with superconductors. What is a conductor? All I'm going to say is at the classical level. Let me say that. So what is a superconductor? So a superconductor is a material medium such that these constitutive relations hold. And these constitutive relations tell us how the material reacts to an externally applied electromagnetic field. So how reacts it? It reacts by generating currents within the material as a response to the fields. And we can write those relations like this. These are actually gauge invariant, or like this, which is actually the gauge invariant version of something which is called London's equations, or London's equations for superconductivity. But these are actually the equations of a diamagnetic material. But a diamagnetic material presenting Meissner effect is actually a superconductor. All superconductors are like that. So the Meissner effect is actually encoded in these relations by setting up this one, because actually the real constitutive relation would be something like this. But Meissner rejected this term of not being zero as unphysical. So really, within these equations are all the physics of classical superconductors or macroscopic superconductors, as we understand them. And the cool thing about superconductors in terms of geometry is that these are represented in terms of fields which are eigenvalues of their curl operator. And that can be written like this. And these kind of equations define a set of fields or a class of fields in vector calculus, which is called the Beltrami fields, which are basically those fields which are parallel to its own curl, right? So these are actually really cool fields that appears in superconductors, plasma physics, and many other applications. These kind of cholesteric crystals, etc. So, but what really is a constitutive relation? So I'm going to build up this talk. So I'm going to go from the very basic, and I hope I managed to convince you that there can be self-gravitating superconductors and all this. So let me begin with a constitutive relation. So what is a constitutive relation? In the gravitational community, at least in my experience, we didn't often work with material medium. Our medium is space-time itself. But when we work in materials, we actually have to take account of constitutive relations and how the material reacts to different stimuli. So let me begin with electromagnetism as a set of postulates. So to formulate electromagnetic theory, we need at least two postulates. We need to postulate that the electromagnetic flux is conserved and the total charge there is in the universe is conserved. So we postulate in an integral fashion like this. And then by means of Stokes' theorem, we can transform these fluxes into sort of divergences. And the conservation laws that we actually postulate are df equal to 0, which is very familiar to everybody, and dj total equal to 0. So these are conservation laws that we use as empirical postulates, right? And the first equation actually tells us these sourceless equations, and it's the one that relates the field to the gauge potential, whereas the latter one is the one relating the currents and the sources to the induced electromagnetic fields in the medium. So in terms of ordinary vector calculus, the first two are the sourceless homogeneous Maxwell's equations, which are equations for E and B, where the second pair is the inhomogeneous Maxwell's equations, which are equations relating the sources and the induced fields. And the problem is, given the external sources, which happen not be the total charges, so the external alone, the problem is, given this information, we need to determine these fields. And that problem is obviously unsolvable because these two sets of equations are actually independent. So we need to postulate more relations connecting these sources to these fields. So we need to postulate some of the things. And one of them is that the external sources do not mix with the induced sources. And together they add up to the total budget of charges sourcing the field. And the induced fields in the material are actually a function of the fields, of the fundamental fields C and B. There are many, many constitutive relations, and all the material science you can actually learn goes into understanding and finding these relations. But the simplest one, the one we're most familiar with, is the metric constitutive relation. That is, if we have a metric, then we can take the Hodge dual of F and obtain G. So that's the usual path we actually take. And this is the simplest one, really, because these relations can be way more complicated and have much more degrees of freedom that they are contained in metric. So there's a very rich area of understanding in terms of material science and geometry and non-metricity and stuff like that. But if we consider a sourceless, the sourceless case, where there's no external sources, then all there is the material reacting to the fields we apply. So we only have induced currents in the material. And the induced currents in the material are related themselves to the fields. And you do that all the time when you set up Ohm's law of classical electromagnetism, where the induced current is just proportional to the field, right? So London's constitutive relations are the relations we're using instead of this relation, which is Ohm's law. So London's equations that we are the ones we started with are the constitutive relations relating the induced current with the fields. This is how the material reacts to the field, to an externally applied field, right? So these are the constitutive relations. All right, so what does it have to do with all the rest of the things? So let me tell you a little bit about contact geometry. Beltrami fields are actually ubiquitous in contact geometry, and contact geometry is a growing branch of mathematical physics that you should know about. So what is contact geometry? Is the study of contact manifolds. And a contact manifold is simply a differentiable manifold, which is odd dimensional. So that means it cannot be a symplectic manifold, and it cannot be kind of a complex manifold itself. But not only that, it's an odd dimensional differentiable manifold together with a non-integrable distribution in its tangent bundle, such that this distribution is generated by the kernel of a one form which satisfies globally this relation, which is basically a volume form. Right? So if you're familiar with symplectic geometry and integrable systems, this may look similar to Frobenius theorem. It's just that it's exactly the opposite of Frobenius theorem. An integrable system is one for which this thing is actually equal to 0. So in our case, this is actually the complete opposite of Frobenius theorem. So this defines the complete non-integrability of this distribution of the tangent bundle. This might be the most abstract part of the talk, so I hope I don't lose you. So to understand what does this integrability means, let us consider a space. Let's say this block, right? And if the block is integrable, it means that it can be foliated by independent surfaces. So each surface is generated by two directions in which you can move freely. So if you start at the point A, say, and the system is integrable, the only directions allowed for you to move are these horizontal directions, and you can go all over you can cover all this surface sigma 1 without any problem, but you cannot reach this other point B, which is in another floor, because it's in a different surface, and you're not allowed to go vertically, right? So that will be a system which is completely integrable. So what non-integrability means is that you can connect actually any 2 points in this manifold by means of horizontal motions only. So obviously that won't be local. So say I want to go from A to this point B, which is right on top of it. But I'm not allowed to go straight to it, like in a vertical direction. If the situation is like this, then I cannot reach B because I'm not allowed to fly. But if I want to do it, then what I do is I can put a stair over here and go here and climb through here and then come back to there. Or I can do it otherwise, like putting a stair over here and then connecting it over here. I mean, there are many ways that you can actually place non-integrability on all these things. And these non-integrability issues are actually quite relevant in control theory. This is exactly what people in control study for controlling systems in engineering. But the good thing about these things, among others, is that this is very similar to the symplectic case, where you have Darboux theorem and you can place coordinates in every contact manifold. Every contact manifold looks locally the same. And all these surfaces are generated by a set of directions, which are termed the horizontal directions. And the whole tangent bundle is comprised of the vertical and the horizontal directions. So why do we need this? I mean, why all this abstraction? What is it good for? So in control theory, we actually want to go from state A to state B, and probably want to do it in a very efficient process. So regarding the shortest horizontal path connecting two given points in that space become relevant. And that is indeed the case in, say, thermodynamics, But in here, let me just say that that's enough motivation for studying contact geometry, and let's jump straight into it. So if I want to know what the shortest, what is the shortest horizontal path, then I need to place a metric in it, and a metric that is nicely stitched into all of the structure defining the contact structure. So a contact metric manifold will be this whole thing, which includes the odd dimension manifold, the distribution, the one form generating it, a structure which is akin to the almost complex structure in Kähler manifolds, and G, which is the metric which is compatible with all these structures, and that's about it. There's an extra piece of information that is given this one form. There's actually one privileged vector field, which is called Rib vector field, which is kind of the tangent bundle equivalent of this one form. But apart from that, this is the structure. This is the most abstract part I will actually go. So what does it all have to do with superconductors? So let me consider the simplest contact manifold you can actually conceive. Well, probably not the simplest, but at least the simplest class, which is the lowest dimensional possible. And the lowest dimensional contact manifold will be a 3-dimensional manifold. And since we're doing gravity, let me consider this G as a Lorentzian metric on that manifold, just to see what happens. And so we're considering the case, the 3-dimensional case because it's the simplest, and the Lorentzian because we like gravity. But in this case, if everything is stitched together, and you want to find it in the literature, you have to look for Parasasakian manifolds, which is kind of the equivalent of Kähler manifolds or para-Kähler manifolds in complex geometry. So all Parasasakian manifolds, which are Lorentzian, happen to satisfy this relation, right? That's a statement. That's a theorem. I don't know what it is. It is what it is. And so what can we do with this? So we can have a look at this relation and then think, all right, but I want to do electromagnetism with it, because why not, right? It will be 3-dimensional, but let's do it anyway. So let us consider a current, or that the induced current in the material as a response to an external field is a vector field and tangent bundle, right? And it wouldn't be any vector field, but it will be a field directed along the direction of this spatial vector field associated with the contact structure. So we're stitching the induced currents to the contact structure itself, right? But contact geometry is better understood in the cotangent bundle. So let us convert this vector field into a one form. You can do that using the metric. So by using the metric, we convert these into that. And we take dual because currents are n-1 forms. And the conservation law we imposed for electromagnetism is actually imposed in current densities. So the current density we have is completely written in terms of geometric quantities defining our contact manifold, and this gauge function over there. That gauge function, by the way, we can sort of reduce it so it looks like kind of a harmonic field, and it is indeed a harmonic field if we consider that the current is conserved. So conservation of charge tells us that this gauge function is actually harmonic. This will be a straightforward calculation, so you can actually do it in your spare time if you want. So what we have locally is that this 2 form, which is the induced current, is related to the induced fields in a conductor, which in turn are related to the external fields by means of the constitutive relation, which is the metric constitutive relation. That's why we need the metric. And if we do this, then we can write this same equation in terms of in terms of a cohomology class, which suggests that we're sort of making a gauge theory of this whole thing. And shortly after that, I'm just presenting the equation, so don't pay no attention to the steps. We arrived at this equation. But this equation happens to be the exterior derivative of the induced current. This is a gauge function, and it's written in terms of the field. Now, if we think about it for a second, the constitutive relation that we have for a superconductor, which are written in terms of this combination of derivatives, look at them for 1 second, and then you can convince that you're actually talking about the exterior derivative of J related to the field. Right? So that is exactly what we have there. And you can actually prove it by using components or whichever way you like. But this equation is basically London's equation for superconducting fields. And we still have this gauge freedom, but it turns out to be that this has to be 0. And that was exactly Meissner's argument. So we set up this gauge function to 0, then we actually arrive at London's equations exactly, right? So this is the gauge independent version, but we can go to the gauge dependent version just by recalling that F is just dA and then just regrouping the entire thing. And this is the gauge dependent London equation. So what we can extract from this is that whenever we're looking at the 3-dimensional Parasosakian manifold, which can be classified really, what we're really thinking is about a geometric equivalent of a superconducting medium. Right, that's pretty cool, except for the fact that it's 3-dimensional, right? But, I mean, it is what it is. Right? So we understood something which is related to contact forms and contact geometry, and a classification in terms of metric and geometry of a full class of materials, superconducting materials, right? So this is on itself might be cool and interesting for some people working in material science, but we can do much more than that. And since this is a gravity meeting, let me go on and complete this part here. Sorry about that long trip. So we already know what a superconductor is and how it's related to contact geometry. But let me put it to self-gravitate and let me see what I can extract from a material point of view. Right? So let me begin with an example. I'm just going to make an example, which is actually useful when you work in contact geometry. Contact geometry is sometimes very abstract, and having nice examples that you can actually touch and feel is very useful. So let me consider S3, the 3-dimensional sphere, together with a contact one form and a metric, which I'm going to tell you what it is in a minute. So the one form we're using in this sphere is written like this, where psi, theta, and phi are the Euler angles for S3. And what I'm really thinking about is the Hopf vibration of S3. So in this case, the Rip vector field associated with this contact form. So just so you remember, these two things are kind of the same thing, just one is in tangent bundle and the other one in the cotangent bundle. So this is the actual field corresponding to this form. Is tangent to the S1 fiber of the Hopf vibration. And the other, and the directions defining the contact distribution, the P's and the Q's, are written explicitly like this. Now, this is actually very cool because if you work in contact geometry, and in this particular basis, you'll find that this vector field satisfies this particular algebra. And those of you who like quantum mechanics will like to see that the Lie bracket of P and Q just gives you the vertical direction, while the vertical direction commutes with all the others. And this algebra it has a name, it's the Heisenberg algebra for these generators. But we also need to place a metric in it. And we have a number of arguments of why using the metric I'm just going to present. I'm just going to use the sort of natural, so to place a name on them. from the space-time point of view. So I'm going to think that the P's and the Q's are null vector fields. So I'm certain that the metric is Lorentzian. And since the metric is well stitched to all the structures defining the contact geometry, then that means that the Reed vector field is normalized, but not only that, it also means that it is space-like. So our metric has the properties of having P and Q as defining the null structure. So P and Q define the null cone for a theory, whereas the Reed vector field, which is the direction we're putting our current, our induced current to flow in, is space-like. So the one metric satisfying these relations in 3 dimensions, which is non-trivial, is this. Well, that's good enough. I'm not gonna tell you a lot about the particular form of this metric, other than a few of its properties. First is non-flat. So it is non-flat and it is not maximally symmetric. It doesn't have any singularity. And it satisfies something very similar to the maximally symmetric spacetimes, which are the Einstein spacetimes. These kind of spacetimes satisfy this relation in which the Ricci tensor is proportional to the metric, but also to the tensor product of the one form defining it. And these manifolds in contact geometry are called eta Einstein. And these are pretty cool because in higher dimensions, these happen to be solutions to the vacuum of Einstein-Gauss-Bonnet theories. But we're not in higher dimensions, and I just think that this is a really cool property for the metric. But also has a number of Killing vector fields, which is B1, B2, B3, and B4. And independently of how they look like, they do have a nice interpretation in contact Hamiltonian formalisms. They do satisfy these algebraic relations. And this implies, I mean, this is a subset of the Heisenberg algebra. And these other brackets implies, and this is a theorem, that G can only be one of 3 possibilities for Lorentzian left and Heisenberg metrics. Heisenberg metrics in terms of the Killing vector field satisfy the Heisenberg algebra, right? So this metric is left and right Heisenberg metric, and there are only 3 possibilities. One of them is Minkowski, and this is not Minkowski. And the other one is excluded because in the other one, the Reed vector field is time-like. So this is a unique metric in this sense. And it hasn't been explored, so it's kind of a new metric on its own. But let's see if it's actually a theory of gravity that we can place on it. So it is indeed a space-time with Lorentzian, it's a metric, but let's see if it actually satisfies some gravitational theory. So for the last part of the talk, I'm just gonna tell how self-gravitating superconductors behave. So recall that in terms of geometric structures in 3 dimensions, a superconductor is basically encoded in a contact metric structure satisfying this relation. So basically a Parasesaki manifold. I'm modifying this a little bit with this extra constant, which will later have the interpretation of the penetration depth in a material. It really doesn't change anything apart from the normalization of the Reed vector field, but it doesn't change the physics at all. So to begin with, G is a solution to a general topological quadratic gravity in 3 dimensions. So if we consider this action, which is a vacuum action, the metric we have is a solution provided the cosmological constant is a function of this penetration depth parameter, and the other 2 coupling constants are basically satisfying this algebraic relation. So that's a nice property. But it's not only that. So among all the topological theories, quadratic theories in 3 dimensions, new massive gravity is kind of appealing because it goes free and people kind of like it. So we try it as well. So it's also a vacuum of new massive gravity, provided the cosmological constant, again, is a function of this penetration depth of the superconductor. And M, which is basically the mass of the massive gravity modes in theory, is also defined in terms of this L. So this begins to look, yes?
5 minutes.
Excellent. I'm going to finish in a minute. So this actually looks appealing from the point of view of some material scientists modeling superconductors, because these massive modes may be interpreted to the massive modes of the propagating degrees of freedom in the superconductor. So anyway, this may actually have a nice interpretation in material science. So, all right, so we have a metric, which is a vacuum of this series. But we're not really having a superconductor, an electromagnetic field on top of it, self-gravitating. But we can put it anyway. So we can do a self-gravitating electromagnetic field by considering the Maxwell-Chern-Simons action. So that will be the new massive gravity action with an action with the Maxwell-Chern-Simons term. So the Maxwell-Chern-Simons action is written like this, basically, which in 3 dimensions is very nice, because this term over here is just the helicity of the contact bond form. And there are many nice and cool results regarding helicity in 3 dimensions. And our geometry is a solution provided that the coupling constant is again given in terms of the penetration depth, the cosmological constant, and the mass are given by these quite neat and simple relations. But even if you are like really trying to get deep into superconductors in terms of its microphysics, you can go further than that. And there's a nice model for superconductors from the Abrikosov vortex theory, which is basically an abelian Higgs theory. So we can couple the gravitational action to the abelian Higgs model, where again, the abelian Higgs model will have this part, the field part, which is basically the helicity, and the scalar field, which is the Higgs field, and a potential term, where this D is the covariant derivative, which is not only the exterior derivative, but it also couples the gauge potential. And the potential energy is just the quartic potential. So calculations are straightforward. You can actually compute an induced current in terms of the Higgs field, which is complex and it might be a function. But in the simplest case, where the field is constant, the real value, that means phi is simply h, then the induced current is h squared, which is a constant times a. This is not a trivial field because of this term over here. But this happens to be, again, London's equation for superconducting. So this is indeed a superconducting action with massive modes of propagation. So our geometry is indeed a solution for a superconductor self-gravitating, provided that the Higgs field is given in terms of L, same as lambda, and the massive modes. So it may not be terribly exciting from the space-time and gravity point of view, or perhaps it is, I really don't know. But what is actually interesting and relevant for the people working in material science is that this provides you with a direct, clear theory for a medium responds to an electromagnetic field. Or saying otherwise, it's the medium properties that people may be looking for are actually gravitational parameters of another theory. And so I'm gonna leave it here. I reckon I'm already over my time. So thank you for listening, and I hope this serves as an invitation to see gravity not only as this magnificent construction that has allowed us to understand the space we inhabit, but a framework which can be generalized to many other branches of more applied sciences and innovation, which is indeed a way I think some of the gravitational field research can actually go forward. So thank you for listening. Thank you.
Thank you, Cesar. Very nice talk. So we have time for maybe one question, one comment. Okay, if not, in the meantime, let me ask you something very brief. So, do you have thinking, or do you have in mind to apply this formalism, this contact geometry formalism to superfluidity instead of superconductivity?
Yes. Actually, I mean, the real deal is four-dimensional superconductors, right? Materials we could possibly engineer are embedded in the space-time we inhabit. So that would be a really, really cool research for understanding superconductors, but also superfluids. I'm not completely certain that if superfluids actually behave as a Beltrami field, but if they do, then definitely you can extract this. The only restriction you have is that they should be incompressible and they should be parallel to its own vorticity. That it might be the case. I mean, plasma physics is actually the case. So yes, actually this whole framework has been developed within the context of hydrodynamics and magnetohydrodynamics. Full differential geometry. It's actually really cool.
Yeah.
So yes. So the answer is yes. The challenge is all the things I presented depends heavily on the dimensions of space-time. So it only works in 3 dimensions. If you go to 4, first of all, it's not a contact manifold, so you won't be able to have any of these. But the constitutive relation we imposed or we found, it's actually only valid in the 3-dimensional case. So that's kind of a drawback, but anyway.
Okay, thank you. Thank you, Cesar. One more comment, one more question? Okay, if not, thank you, Cesar, again for your nice talk.
Excellent, thank you very much.
Thank you.